Hi, morning to all. Myself Puvi Arasan, and I am going to take a topic on manufacturing technology. We all know that manufacturing technology or manufacturing process is converting raw material into end product using men, machines and materials. And in manufacturing technology, it's broadly classified into 4 categories normally: casting process, forming process, fabrication and material removal process. Out of which the last one, material removal process, contributes more than 35% of entire share in manufacturing technology. And this material removal process is essential when we go for or when we need higher surface finish and closer tolerance. Sometimes it's very difficult to obtain a different complicated shape by means of some other process. In that case also material removal process is important. In material removal process, theory of metal cutting is a very important topic since this theory of metal cutting deals with material removal mechanism and various relationship between cutting forces. This topic is very important. Yeah, in theory of metal cutting, actually we have 2 things. One is thick shear plane model, another one is thin shear plane model. In case of thin shear plane model, we do assume that the material shear plane is thin in nature. Right. Before that, we should know about the simplicity in material removal process. Yes, in the material cutting removal process, the analysis about cutting forces are important since this contributes more towards performance in material removal process. Naturally or normally, common processes like turning or milling involves 3-dimensional cutting. That means oblique cutting. The obliquity comes between angle between cutting tool edge and the cutting tool velocity. Cutting tool is moved in this direction, that's cutting tool velocity, and cutting tool edge direction. So this obliquity causes for some difficulty. That's why we do simplify in it that orthogonal cutting. In orthogonal cutting, the movement of cutting tool and the cutting tool edge is perpendicular in nature. Hence, for this analysis, we do assume it's orthogonal cutting. Alright, in orthogonal cutting, we are going to discuss about mechanics of material removal. When the cutting tool is moved in a particular direction that exerts some force Fh or Fc in horizontal direction, in this direction it acts as some force, and this cutting tool forces can be related in a circle. This circle is commonly called as cutting force circle or Merchant circle. Let us have a small discussion on this Merchant circle derivation. In a orthogonal metal cutting, we have 2 schools of theory. One is thin shear plane model, another one is thick shear plane model. In case of thin shear plane model, this is applicable for cutting action which takes place in higher cutting speed, which uses minimum energy principle. It means shear takes across this thin line, which is called as thin shear plane model. Using thin shear plane model, we are going to discuss the various relationship between cutting forces. It's a shear plane, and the angle of shear is represented as pi, and it's my cutting tool which have a back rack angle of alpha, and this is my clearance angle, and of course this is the workpiece. Let me isolate this particular chip, and in this chip it's an isolated diagram of chip. In this chip only 2 forces are acting now. One force is between cutting tool and the chip, the other force is between chip and the workpiece. It means R and R dash. To be in equilibrium, this R and R dash are equal in magnitude and opposite in direction. Here this R dash involves 2 forces, Fh and Fv. Fh, horizontal force along the direction of primary cutting tool motion, and Fv, perpendicular to cutting tool motion. This is velocity of cutting tool. So horizontal force is Fh. Normally it's notated as Fh. In some text you may find it as Fc. And Fv is perpendicular force to the primary cutting motion. And here it's F is frictional force between cutting tool and the chip, and N is normal force between chip and the tool. So this is the isolated diagram of a chip, and this all forces can be represented in a circle which is called as cutting force circle, most commonly called as Merchant circle, which is very easiest way to represent the cutting tool forces. So here I am marking those cutting tool edge, and the shear plane is like this, and I am recreating this. It's my workpiece. So this is my shear plane, which is having angle of pi. So pi is shear plane angle or shear angle in simple, and alpha is back rack angle or in simple rack angle. So cutting tool here I can construct which is alpha again, and I am drawing a horizontal line which is FH, horizontal force along the primary motion of the tool, and this is FV, vertical force FV, and resultant of this, of course all this would meet in a single point R, and parallel to this rack face, if we extend further, this line is frictional force F, and this is N, and along this shear plane one force is acting, that is Fs, force acting parallel to shear plane, Fs. And this is Ns, normal force along the shear plane. Right. And remember, this is perpendicular, perpendicular, perpendicular in orthogonal cutting. It's my workpiece. Right. The idea of this cutting force circle or Merchant circle, or the use of cutting force circle, is that representing Fs, Ns and representing F and N in terms of FH and FV. Since it's possible to find FH and FV using dynamometer, the idea of this cutting force circle is representation of all the four forces in terms of FH and FV. So let us have a small relation between various forces. For convenience, I just name this point as O, A, B, C and D. And if this is pi, this is also pi. I will tell you how it will be. So isolating these forces, I am drawing O, it's FH. I can write it over here, and it's FV. Resultant force R and frictional force F, force along the shear plane Fs, and this is Ns. Remaining two forces I have skipped. In the next diagram we can relate that, and of course this is 90 and this is also 90. And remember, and this is shear plane angle pi. In order to complete this triangle, let me extend this further. and parallel to ns, I am drawing this. These two lines are parallel and I have simply extended this. And again a parallel line here. These two lines are parallel. For convenience, I am naming this A, B, same notations that was used here, and of course this is D, so new notations E and F. If this is pi, this will be 90 and 90 minus pi. If this is 90 minus pi, 90 degree, this will be 90 minus pi. Again this is pi. So relating the forces, we can write, first let me find Fs. Fs is OD, which is OE minus D, entire length minus this D. So OE minus ED. OE is here and the horizontal line length is FH. Relating this triangle AOE, we can write the relation for this. So OE is opposite to the FH. So relating with pi, OE side is cos pi FH. It's very simple. Pi is here and this is my hypotenuse side FH and this is my adjacent side OE. So FH cos pi minus ED. ED is here. ED is equal to AF. So AF can be related to AB. AB is, we can rewrite in terms of FV. So AF is opposite to that of this pi angle. So opposite side is sin pi FV. So Fs relation we have found. Similarly for Ns, Ns is this entire length BD. So which is nothing but DF plus FB. DF plus this FB. For DF, DF is equal to AE. AE, we can take this triangle AOE. So we have two triangles AOE, another triangle is AFB. So first triangle AOE relating with this AE side, its opposite side, so that's opposite side sin pi FH plus FB is here, which is adjacent side, so cos pi. So Fs, Ns, we have calculated the relationship for Fs and Ns. Similarly, it is very much possible to calculate relation for F and N. Let me write it here. So we have O, FH, FV, or F and N. This angle is back rack angle alpha, and here to solve for F and N, this F by applying principle of transmissibility, I can move it here. This is my F parallel to this. And again I can move this N here. So it's my N and this is my f. Remember, these two are parallel and these two are parallel. To complete it as a triangle, further I do extend, and parallel to f I am drawing a line here. So for convenience again I can name, so previous notations just I keep as it is, A, B, C, D, E already we have used, D, E and F. So new notations G, H and parallel line I. For forming triangle I have drawn some parallel lines. This is line of extension. This line is already drawn parallel to F and this is also parallel to this. This line is already drawn parallel to N and this is simply extension of this parallel to this N line. And the angle is alpha here. If this is alpha, perpendicular line, I mean vertical line, this inclined line is alpha. Inclined line means F line. Similarly, vertical line, inclined line is alpha. This is alpha. To be clear, this is alpha. So relating this, to find F and N, first let me find N. N is OG, which is OH minus GH. So OH, the entire length, for that I have to relate with this angle. If this is alpha, this is 90 degree and this is 90 degree, 90 minus alpha, 90 minus 90 minus alpha, this is my alpha. So OH, the entire length, again here also I have two triangle, triangle AOH, another triangle is triangle AIB. So considering first triangle, OH can be found in terms of FH relating alpha, that's adjacent side, so cos alpha, so FH minus GH is here, GH is equal to AI, AI I have to find from the second triangle AIB, so AI is opposite side, that's sin alpha, FV. So N value I have found, F value is the entire length GB, so GB is equal to GI plus IB, GI is equal to HA, again first triangle, its opposite side, so sin alpha, it's FH plus IB is here, IB, directly I can relate with the adjacent side cos alpha, so F. And to find friction angle which is between F and N, it's beta. So to find that mu is equal to tan beta, friction angle is called as beta, which is nothing but tan beta is F by N, opposite by adjacent. F value is FH sin alpha plus FV cos alpha divided by FH cos alpha minus FV sin alpha. Again simplify this by dividing by cos alpha in numerator and denominator. So I do get FH tan alpha plus FV divided by FH minus FV tan alpha. So this is for mu or tan beta. Remember three angles, one is pi, alpha, and the last one is beta. Pi is shear angle, alpha is back crack angle or rack angle, and beta is friction angle. Friends, once again I repeat the concept. The idea of this cutting force circle is that finding Fs, Ns, F and N in terms of Fh and Fv, and this Fh, Fv can be calculated using dynamometer, and once again we have some relationship between pi and alpha. Pi is shear plane angle and alpha is back rack angle. That relationship in the next session we can discuss. Relationship between shear plane angle and back rack angle, that's tan pi is r cos alpha divided by 1 minus r sin alpha. And in this relation, using this relation, it is possible to calculate pi, shear plane angle, because there is no practical way to calculate pi. That's why we can use this relation to calculate pi. We know the alpha value, back rack angle, r value, chip thickness ratio between cut chip thickness to uncut chip thickness. Using that, it's possible to calculate pi. Back substituting those values, it's possible to calculate the various forces involved in cutting tool action, which is very useful in analyzing mechanics of orthogonal metal cutting. We have discussed about cutting tool forces, that is clearly represented in these diagrams, and it's a merchant circle. Here we can see this Fh is represented as Fc, cutting force, and it's a vertical force, and pi, alpha are represented here. And this merchant circle diagram is very useful in analyzing cutting tool forces. Hope you have enjoyed this video. Thank you once again.